All right, so our pipe is 4,200 feet from the corner of the building up to the dam. It's 6 foot 6 inch inside diameter. It carries about 2,200 gallons of water a second into the plant. We have 3 Francis machines in this building, and we have a Francis in this building as well, so we have a total of 4 machines. We have 1.5 megawatt output, and that tower is there to release the pressure from the pipe during emergency shutdowns. I can show you guys in here. This one's shut down, so it's a little bit quiet. The water hog, this is the last one on, first one off. It's the least efficient, and this is what used to run this whole building. And this shaft used to go 600 feet the length of the building, and it was belt drywall. This was a weatherboard, paper place, and all the equipment 5 stories up, 2 stories down, was belt driven off of this machine. It's about 1,000 brake horsepower, and this is the original governor for it, because before it was used for electrical generation, they had to govern the speed for their equipment. Now, because we have synchronous machines, the machine or the generator is always spinning at a constant RPM because it's locked in phase with the grid. So it's a 60 hertz system is what we run in the United States, and that will only let this machine run 600 RPM. And belt driven over here. We have the big ship spins 200 RPM, the small one spins 600. And this is the only belt driven machine, but you can see how it's been modified. That shaft used to go all the way through. There were never any block walls there. It went 600 feet through the entire building, and everything was run off belts like this.
And this was a paper mill?
Leatherboard. Leatherboard. Paper type material. And they actually used to drive the train right into this building, because there's a train track up there, and they used to come in on the 3rd story with the train.
Wow.
And dump everything off. And this was the equipment. And we, because these are synchronous machines, when you put them online, you have to get them right to the right frequency before you close the breakers, or you get a massive influx of power to the grid, or if you're going too slow, into the building. And it's pretty dangerous if that happens. And these they're electromagnet, they're non-fixed magnet machines, so we have to apply a 48 volt DC current to the generator to actually get our 160 volt output out of it. So we have it's basically a giant car alternator, and it spins at about 1,000 RPM and creates our DC voltage for this machine. And each machine has one of these, but most of them are static state, so it's a solid silicone thing now. These are the old-fashioned way of doing it with the alternator. And we've got a 48 volt DC backup in there, and we have, because we're over a megawatt, by law we have to have a pole-mounted circuit breaker. It's called a recloser. And you see the big square things on. When you see a square-looking transformer on a telephone pole, it's a recloser. And what happens is a branch goes across 2 lines, creates a short, and then it normally either vaporizes whatever caused the short or breaks the line. And the recloser will open and then automatically try and reclose every couple seconds for 30 seconds, and then you got to manually reclose it. So.
So what happened, for example, did you have to go offline during the hurricane?
No, but there was so much, we sell our power on an ISO grid. It's a 5-minute basis, so it's just like the stock market, but it changes every 5 minutes. And what they do during emergencies like that, when there's so much power, so many power lines down, and there's still so many people producing electricity, there's nowhere for the electricity to go. So what they'll do is they'll drop the price to 0. So we're still producing electricity, but we're not getting paid. So it's an incentive for power plants to shut down. So a lot of the larger power plants will actually turn off because you're not getting paid for your electricity, wear and tear on machinery and stuff like that. So during the hurricane, for about a 12-hour period, we were still producing electricity, but we got 0 for it.
Nice.
Yeah. That's what I like to do. Yeah, just this is our accumulators. This is how we shut. Every machine has one of these. And they look different, but they're all function about the same. And this is a nitrogen pressurized tank, and we keep about 1,200 psi of pressure. It's got nitrogen with hydraulic fluid on the bottom of it. And when we shut down or we lose power, there's an electric solenoid that opens and releases that hydraulic pressure to hydraulically shut down these machines. So you don't need power to shut down. It's the whole idea behind it. And if you didn't shut them down, they would just go faster and faster until they blew themselves apart. Water goes through the Francis turbine, comes out the back side of the turbine, goes down through the floor, and comes back out into the river. And this is a 1942 or 1941 generator that came out of a World War II ship, a Navy ship. And that's 280 kW right now machine. And it was rebuilt in 1998. How long have you guys had this ship? A little over a year. It's a 1987. It's the most powerful machine, even though it's the smallest, because the efficiency has gotten. These machines are about 80% efficient, and this machine's about 91% efficient. So they only got 11% more efficient in 100 years. So the technology really hasn't gotten that much better. This one is a 550 kW machine. It was made in France. So it's a pain to work on. Everything's metric. It's just not as good as the old one. I mean, it's the same thing except for it's vertical. Like this one could be horizontal or vertical. It doesn't matter. It's the same. And this is where the water comes in. That big pipe right there is the original diameter of
this pipe here is going to that machine up there, huh? What? This yellow pipe is going to the machine up there?
Yep. And it's about 50 psi of water, and it's a 48-inch diameter pipe. Wow. It's a lot of water that goes through this pipe. That was a grist mill. This place used to be a grist mill, and then they moved the dam up to a better location, about 4,200 feet up from here. And then from 1910 on, it was run from up there. But that dam up there, our dam that we're still using, was put in the 1850s. So it's a granite block dam with a cement cap and wood stringers for the stop block, so we can control the level of the pond. And that actually, I forgot to mention, the new machine is computerized. The old machines, I need to come in and change things, and they kind of set it and forget it. The new machine has a transducer up at the pond. So when we get more water and the flow starts to come up overnight, that machine will increase its output automatically and accept that water, so we don't miss that revenue at night. And these machines make enough heat that we don't need to heat the building either while they're running. We can go upstairs to number one. We have redundant fuses. We have a main breaker there. There's 3 fuses because it's 3-phase power. And then we have redundant 3-fuse system up on the poles. So when we get like a swirl or something on the pole, if it goes from what they do a lot, is the swirl will be sitting on the top of the transformer, and the transformer's grounded. And then the high side, so it has the ceramic bushing, and then you see the wire coming out the top of the transformer. And what they do is they'll stand on top of the transformer and reach up and grab that wire to jump on the wires. And if they make that connection between the two of them, they got 34,000 volts through them, and they just go poof, gone. Instant vaporize. And they blow the fuses in here. And you go outside and they'll just be like hair floating around. But they're, for the most part, they're safer for the person inside using it. It was top of the line when it came out, because the other old ones are 200 RPM machines, and this is a 600 RPM machine, which from 1910 a 600 RPM machine was unheard of. And it's a Francis as well. It's only got a 21-inch diameter wheel, and it's this big, and it does 350 kW output, so 0.35 megawatts. So it puts out a lot of power for a tiny little runner, and it's very efficient. And this machine right here, most of our machine or generators, they're either General Electric or Westinghouse, even though General Electric wanted the DC thing back in the turn of the century. They were still making AC generators. The nameplate on this is 250 kW output, but this machine will actually do 350, and it's because it was rewound. And the modern insulation on the copper wire is that much thinner and that much better that they can fit that much more copper inside the transformer, inside the generator itself. So the machine had the power to turn it, so we're actually getting more output out of the same machine.
And how old did you say that was?
This is 1910.
Wow. So over 100 years old.
It was it was made in 1909, installed in 1910. And it came over on the rails. And this is the same thing with the accumulator. This is the hydraulic accumulator. It's pressurized nitrogen with hydraulic control. So if we lose power, we still have hydraulic controls to the machine. And it's got the same setup as number 3, where this whole wheel spins like that, which simultaneously adjusts all the gates in there. There's fins on the inside of each one of these linkages, and they all spin together. And this is, again, back bearing, no roller bearings, no moving parts, and that's why they last so long. And we've also got, they've got shatter protector things that detect any abnormal vibration, and we've got temperature probes on each one of them. So the computer monitors all our temperatures, all our vibrations at all times. If there's anything that goes out of the norm in their preset settings, it'll set off an alarm. I'll call my phone. And then if I don't get here in time and it keeps getting worse, or it's getting hotter, or something's going on, the computer will take over and start shutting down machines. So it's a pretty good system. And then just put it in the 80s, but it was actually an air conditioning system for large buildings in Boston, and somehow they modified it to control a hydroelectric power plant. They were smarter than me. This is our when this program was actually written, because every program has to be written for an individual site. This was written in like 1984, I believe. So it was written on like a green screen DOS, like POS computer, and this is the original program. So we have to have a DOS program running inside this. So we had to modify the computer and everything to be able to accept it, but it's advanced enough that I've got my pond level down to 1/100 of an inch. So if I can detect changes that are, you go up there and you look and you can't see that there's been a change in the pond level, and the computer's picking it up. And I've got the outputs of each of the machines, every bearing temperature, the room temperatures, which is important in the winter so nothing freezes up. And I've got control over this at home and here. So I can be at home and I can look at this screen. I can go into it and go across and open up any of the individual bearings, look at what their temperatures have been doing over the last couple of days. It was really well written program for back then. I think they said they spent $40,000 writing this program, and it's still running, so it's obviously was worth it. And they wanted to, we looked at getting a new one just to have a more modern one, and it was like $100,000 to write a program like this. So why fix it if it's not broken? And this is just regular computer, but I've got I can go in here and I get the flow of the river, so I know that this is the flow of the river, and the dam up above us is a state-controlled dam, and they manage it recreation purposes only. No other consideration in the state of New Hampshire and state-run dams except for recreation. Like they had a kayak event and they want to get a whole bunch of people out there kayaking, they'll just open that dam and just dump 1,000 CFS down there for like a day, and then they'll just shut it off. And they screw with the environment more than anyone does. They do ridiculous things. Like look at these, that's all those sharp angles and moves are just them just in an office in Concord messing with it.
I'll be sending them a copy of this video.
No, don't do that.
No, I'm just kidding.
We're trying to be friends with them.
I'm just kidding you.
No, but they've been working with, like, in the summer we also have the reservoir level, and they have the summer water level, and then this time of year they bring it down. And we've actually worked with them because they used to just open it and just dump water, and now we've got them so that they'll do it at more of a gradual rate so we can actually generate power with it, because when they dump all that water, it just goes right over the top of the dam and the pond's empty in no time, versus when they do a gradual release, we can use the power and there's no threat of erosion and everything else. It's much better done gradually. It's just pretty much true with everything.
And how much, if any, warning do they give you for these changes?
Sometimes they don't give you any warning and the computer just calls me and there's a high water alarm and I gotta fly up here 90 miles an hour and open the dam. Sometimes they'll cut it off and all of a sudden I get a call on my phone, and all the machines are shutting themselves down. They don't know what's going on.
No longer.
Yeah, but as of lately, they've been giving me about a day's notice because we made a big stink about them doing stuff. And they could damage our equipment by doing stuff like that.
Sure.
But they've been pretty good since we had a big meeting with them.
Yeah, we had to go up there and have a big meeting with them.
I don't think they really understood.
No, they really didn't understand what they were doing downstream. And we're only one of a lot. I think there's 5 hydroelectric dams on this river.
What river is this?
Great Bay. This is Salmon Falls River.
No.
So we've got Milton 3 ponds up above us, and they control all the water release. And then there's us, which is the first hydroelectric dam, but there are 2 dams in between us and them. And then the next guy downstream, which this, where you can see right here, kind of goes out into a lake. Right there, that's Spalding Pond, and there on the back side of that lake, there's a dam, and that's a hydroelectric reservoir right there. So we're literally putting water from this hydro plant right into the next hydro plant, and that just keeps going all the way down to Great Bay. So this Salmon Falls River historically has produced a lot of power, and there haven't been any salmon here for a very long time, obviously, but we have a wicked healthy population of eels, and they come up. We don't have a fish ladder on our dam. We're not required to because the 8 dams downstream don't have them. And eels don't need fish ladders. Period. Bottom line, end of story. As much as all the guys in the DES talk about how they want to push it to be an endangered species so that you have to have passage for eels, if you go up there at night, they just go right around the dam. They come up to the dam, they go right through the woods, and they go around the dam, and they pop out on the other side. They have no problem with it.
Really? Wow.
Yeah.
So all the flow from the river's coming through here?
No, not all of it. We have we spill our minimum flow over through. That's the river right there,
Okay.
and this is just what's coming out the back side. And we have a minimum flow, but the state dam doesn't have a minimum flow, so it's kind of like, you know, they do whatever they want to do, whenever they want to do it. Oh, yeah. You guys want to go through the dam?
Yeah.
Can pass 10,000 CFS, which is more than the upstream dam can pass, so they've got to get wiped out before we get wiped out. So we're pretty good. These are our intakes, and this is our 6-foot diameter pipe, goes straight shot like that through the woods, underground, and these are our head gates. And this is just a big hydraulically operated gate, shuts off the pipe if there's a rupture or any sort of emergency. We can come up here and kill it at the source, and just for maintenance as well. But when in the fall, this is like gets dump trucks loads of leaves. Like you wouldn't even believe it. A windy day in the fall, you're up here all the time. And these trash racks are that's probably 25 feet wide or so, and it's about 30 feet deep. And at the end of this boom, there's a brush, and these are they're the best trash racks I've seen. I've been to a lot of plants. And it'll do this whole grate in one sweep. And most of the ones that you see at the other sites, they have to go sweep, 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 and work their way across. And I can do one and done with this.
What does it sweep everything up onto here?
It sweeps everything up here, and I just use a snow shovel and push it all right off the backside of the dam. And by law, we're not supposed to pile any of the stuff on the shore bank, so everything that comes down the river has to go back into the river. So.
And this is what's not going into the power plant. Is that correct?
This is our minimum flow.
And that's set by law?
Yeah.
Or by contract with you?
Well, by contract. Not really law. It's typically a contract is about half a cubic foot per square mile. drainage area.
And what's the drainage area? The area of the pond above you here? Or?
Well, our drainage area is manipulated by culverts and stuff like that, but historically our drainage area is about 100 square miles.
Oh, I got you. Okay.
So now because water's diverted from area to area, and sometimes someone will throw a culvert in that might divert 10 square miles worth of drainage out of the watershed. So if nothing was touched, it would be about 100. And over on this side, basically remove it. Got an hour or two. And this is so that we don't need to dismantle it. Our leakage is almost minimum flow. And this is all granite block capped in cement with those pressure treated struts to hold it up.
And what is this called here?
These are the waste gates. This is just where we let excess water go during floods or a storm, or just so we don't need to manually take the dam apart. And this whole dam is backed up with a generator over there in the building, so we have.
Just went to Maine.
Yeah, and that's Maine, and this is New Hampshire.
Yeah.
And during hunting season, which is right now, a lot of people do a lot of, or New Hampshire hunters hunt in Maine, and Maine hunters hunt in New Hampshire, and they drag their deer across this.
Oh, really?
Yeah, because the laws are different. I don't know. You come up here and you see bloody drag marks across the dam.
Wait, so that's Maine right there?
Yeah.
Huh, that's cool.
Yeah, this Salmon Falls River is the border between Maine and New Hampshire.
There's a high water mark on the Maine side.
Yeah, I guess that's probably
I think that's how it is on the Connecticut River. They own New Hampshire owns the high water mark on the Vermont side.
I know that for fishing game purposes, if someone's fishing in this body of water and they're on that side and they have a New Hampshire license, they're safe.
Yeah.
But I don't know where
and you go over there, you get in trouble.
Yeah, something like that is. But fishing here is awesome. They're huge bass in here. And down on this side, they stock the stream, or they stock the pond upstream with trout. And they open up their dam and they have under dam passage, and we typically do over dam passage. So they just open up big pipes underneath their dam, and it sucks all the fish and everything out of their pond, and they all pile up in here, and they can get back up during like extremely high flow and stuff like that. But for the most part, we get a concentration of like really good fishing here. Everyone comes here to fish. And right down here, sometimes in the fall, in those pools, you'll see a lot of brown trout in particular is the big stock.
And our trash rack spacing is 3/4 inch, so we don't, nothing will go in there.
And we have less than 1 foot per second of flow. So that's one of the qualifications for green energy, so that you can't entrain anything on the racks. So regardless of the fish species, in theory, there's no way they could get suction up to the rack, because they'll always be able to overcome that current. And that big yellow boom is just an effort to divert most of the leaves and debris that comes down the river over the top of the dam versus
Through your sluice.
into the racks, so that someone has to come up here and clean it. And they worked really well. Came from the BP oil spill.
Did it?
Yeah.
Although it was new, we'd never had
It didn't have oil in it, but it was
that's
surplus.
what they used, Works great to keep the leaves out.
Yeah, it stops 90% of what comes down the river. You take it out, and we've got to take it out soon because of the ice. And like overnight, you get 3 times as much junk on your trash racks.
Do you go in the water to take it out?
Oh no, I'll just pull it out from over there on the shore.
All right.
We do swim here occasionally to fix stuff on the dam, but not this time of year.
Yeah.
We can wait.
A half cylinder in the bottom of them.